ME204, Introduction to Units. There's some basic quantities that we use in mechanics. These include length, time, mass, and force. Time is something that we're going to use in dynamics frequently. It's how we measure how fast an object is moving or how fast it's accelerating. Mass is related to weight by a gravitational constant. And force deals with the push or pull on an object. It has magnitude, direction, and a point of application. In engineering, we commonly use two different systems of units for our units of measurement. We have the SI system, or the System International, which is also known as the metric system. And then there's also the US customary, or English units. The commonly used units of measurement deal with length, time, mass, and force. For length, in the SI system, we typically use meters as the base unit. This can be represented with a small m. In the US or English system, we use feet, which is represented by ft. For time, typically the base unit is seconds. In the SI system, we use a small s to represent that. And in the English system, we also use seconds with a small s. For mass, in the SI system, we use a kilogram as the base unit, which is represented by a small k, small g. In the English system, we use what's called a slug, and we represent that with the same word, slug. For force, in the SI system, we use a newton. We represent this with a capital N. And in the US or English system, we use pounds and represent that with an lb, and sometimes we'll see this as lbs as well. Note that these units, length, time, and mass, are base units. They can't be broken down into anything smaller. Force is made up of a combination of units, a combination of the base units. For example, a newton is a kilogram meter per second squared, and a pound is a slug foot per second squared. For the SI system, when we talk about the gravitational constant, we're talking about the acceleration of an object due to gravity, or the gravitational pull of the Earth. We use a value, g, that has been found to be 9.81 meters per second squared. A force is represented with a newton. But a weight is also a force. A weight is equal to a mass times an acceleration, but in this case the acceleration is the acceleration due to gravity, g. If we have a 1 kilogram mass, and we multiply that by the gravitational constant, 9.81 meters per second squared, then we get 9.81 kilograms meters per second squared. But by definition, we know that 1 newton is equal to a kilogram meter per second squared. So we have 9.81 newtons. In other words, a body of mass of 1 kilogram has a weight of 9.81 newtons. In the SI system, there are some prefixes that we commonly use that we should be familiar with. A capital G represents giga, which has a multiplication factor of 10 to the 9th power. A capital M is mega, which is multiplied by a million, or 10 to the 6th. The symbol small k is a kilo, which is 1,000, or 10 to the 3rd. A small m represents a milli, which is 0.001, or 10 to the minus 3rd. Mu represents a micro, which is 0.000001, or 10 to the minus 6, and a small n represents a nano, which is 10 to the minus 9th. These prefixes can be added to our units in the SI system to expand or contract the value of what's being measured. For the US customary or English units, our gravitational constant is 32.2 feet per second squared. This is the acceleration due to gravity in English units. If a mass is a slug, and a mass is defined as a weight divided by gravity, then if we have a weight of 32.2 pounds, and we divide that by our gravitational constant of 32.2 feet per second squared, and if by definition a pound is a slug foot per second squared, if we have 32.2 divided by 32.2, we get 1 pound second squared per foot. But again, the pound is a slug foot per second squared, so our feet cancel, our seconds cancel, and we're left with 1 slug. Or in other words, a body of weight 32.2 pounds has a mass of 1 slug. Now let's talk about unit conversion. Sometimes we have to move from one unit to another, sometimes from one system to another. So true or false, you can multiply a number by 1 and it will remain unchanged. Well, this is true. For example, if we have 5 and we multiply that by 1, then our answer is still 5. True or false, any number divided by itself equals 1 with the exception of 0. This is also true. 5 divided by 5 is equal to 1. How about this one? True or false, any number divided by something equivalent to itself also equals 1. This is also true. For example, a length of 12 inches divided by a length of 1 foot is still equal to 1. Both lengths are the same size, so if we divide them by the same size, they equal 1. This helps us in doing our unit conversions. Therefore, you can multiply any number by a ratio of equivalent units, for example, that 12 inches per 1 foot, so that the unwanted units cancel out and you are left with the desired units. This is the key to unit conversion. We want to be able to cancel out our unwanted units and leave us with the units that we want. For example, if we wanted to convert 5 meters to inches, and we know that there are 3.28 feet in 1 meter, we could write this by putting down our 5 meters first, putting in a conversion factor of 3.28 feet per 1 meter, which equals 1. 3.28 feet divided by 1 meter equals 1. There are 12 inches in 1 foot. This equals 1. So we're really not changing this initial length by multiplying it by these factors. However, once we do this, we can cancel our meters, we can cancel our feet, and we're left with inches. In this case, 196.8 inches. Let's try another one. Let's convert 30 meters per second to miles per hour. Again, our conversion factors, 1 meter is 3.28 feet, and 1 mile equals 5,280 feet. Well, let's start with what we know. We have 30 meters per second. And I'm going to write it in this way so that I have the meters on top and the seconds down below, so that when it comes time to cancel, I can cancel the units out easily. Well, what should we start with? Well, let's say that there's 3.28 feet per 1 meter. This allows us to cancel out the meters. But we're not trying to get to feet, we're trying to get to miles. So we need to use our conversion factor of 1 mile has 5,280 feet. Notice that I put the feet on the bottom so that they'll cancel with the feet on the top. Now I'm left with miles on top and seconds on bottom. So I need to get rid of the seconds on the bottom and convert that to hours. Well, there are 60 seconds for every 1 minute. In this case, my seconds cancel. And there are 60 minutes for every hour, so my minutes cancel. Now I'm left with miles on top and hours on the bottom, so I have miles per hour. Now I can just multiply all of the numbers on the top and all of the numbers on the bottom and finish the math, and I'll end up with 67.1 miles per hour. Here's another one. Let's convert 120 kilopascals to psi. Well, remember that a kilopascal, kilo means 1,000, so it's 120,000 pascals. And a pascal is a newton per meter squared. Or 1 kilopascal is 1,000 newtons per meter squared. That means that we would have 120,000 newtons per meter squared. And that's what we know, so that's what I'm going to start with. Now, let's see if we can get rid of our newtons. If we use the conversion factor of 1 pound equals 4.45 newtons and place the newtons on the bottom, then I can cancel the newtons. Now I'm left with pounds per meter squared. Well, I've got pounds, and that's what I'm looking for on the top, but I need square inches on the bottom. So I'm going to multiply this by 1 squared meter squared per 3.28 squared feet squared. Note that both the unit and the value have to be squared in order for this to work. Now I can cancel my square meters, but I'm still left with pounds per square foot. So I'm going to multiply it by 1 squared foot squared per 12 squared inches squared. Again, note that both the units and the values have to be squared. 1 square foot has 144 square inches, not 12 square inches. Again, we have to square both the unit and the value. Now I can cancel out the feet squared. And what am I left with? Pounds and square inches, which is what we're looking for, pounds per square inch. Once I have it down to the units I'm looking for, I can multiply everything across, and I'm left with 17.4 pounds per square inch. Finally, let's talk briefly about significant figures. It's important as engineers that we know when to stop when we're writing out the numbers that we're working with. We don't want a whole list of numbers that are out several decimal places that we really can't use. So generally, for engineering principles, we use 3 or 4 appropriate significant figures on the final answer. Keep your intermediate calculations in your calculator as long as you possibly can. That way, that helps eliminate rounding errors, and we just round at the final answer. If you have to write something down intermediate from your calculator that you're going to use later on, typically use 4 significant figures for intermediate answers, so that when you get to the end and you round to 3, you're rounding to the appropriate value. Then we round the final answer. For example, we would use 4.78 or 47.8 or 0.478. Notice that these all have 3 values and no more, so we're rounding that third value off. If we have a very large number, we might leave the last number as 0. So we would have 3 significant figures, a 4, a 7, and an 8, and then the last number we would represent with a 0. If we have something really large, we would have a lot of trailing zeros here. Then we can represent that in scientific notation with 4.78 times 10 to the third, rather than writing out all of the zeros. Our next topic will be an introduction to motion.